Hello students, to our last section in chapter 9. 9.16 is the divergence theorem. In this section, we present a second vector from Green's theorem, and its three-dimensional analog. So what we're going to do is we are again in the Green's theorem. What do? We find the flux, right? Okay. In the flux, okay, the divergence theorem says let D be any closed bounded region, okay, and F is the force function, okay, be a vector, and then, okay, this is all continuous. Then the flux here, remember the flux is what? F dot N times ds, right? This is in double integral. We did it in the previous sections. Now I'm going to find the flux in a different way, which is what? Using 3 dimensions, 3 integral, but instead of f dot n, I'm going to replace this one with the divergence of f, divergence of this one, and then dv. So we're going to find the flux today in a different way. Instead of double integral, we're going to use triple integral, and inside, we're going to say the divergence of f dv, and v is the volume of the surface. Okay, dv represents the volume of the three-dimensional surface. Okay, this is our three-dimensional surface. All right. Let's look at this example. Let's find the flux. Okay, verify divergence. Same. What do you say? You say flux is equal triple integration over d of the divergence of f, then dv. Remember, what's the divergence of f? It's the partial derivative with respect to x of p plus the partial derivative with respect to y of q plus the partial derivative with respect to z of r. This is p, this one is q, and this one is r. So it's a scalar function. What's the derivative of p with respect to x? It's easy to see that it is 4. Plus, what's the derivative of this with respect to y? It's 1. Plus, what's the derivative of this with respect to z? It's 4. So the answer is 9. So the flux is equal to the triple integration of 9 dv over d. I'm going to take 9 out. Now I'm left with the dv over the three-dimensional space. What is the d here, guys? It's the sphere, isn't it? Remember, this is 1. So this is equal to 9 times the volume. Look, it's the volume of the surface. My surface is a sphere. So this is the surface. Our surface here is sphere, which is equal to 9. What's the volume of a sphere? 4 over 3 pi r cubed. What's r here? This is the radius 2, so the radius here is 2. So this is times 2 cubed. 4/3 pi r cubed, which is 8, right? So this is 4/3. So this one with this one is a 3. 2 to the 3 is 8. And this is equal to 8 times 12 pi. And if you this one, you get actually 96 pi. This is the shape that we have. We have a sphere, as you know, of radius. I don't have to graph it. So because I know that my D is a sphere, this is the answer of this question. The second one says, verify the flux. Okay, flux. It's equal to the triple integration over the region D of here, divergence of F dV. Let's look at divergence of F, guys. Divergence of F is, here is P, the partial derivative with respect to X of X squared plus the partial derivative with respect to Y of 2YZ plus the partial derivative with respect to z of 4z cubed. And this is equal to the derivative of the first one is 2x. The derivative of y is 1. I'm left with 2z. And the derivative of the last one is 12z squared. This is the divergence. So this is equal to the flux here is equal to the triple integral of 2x plus 2z plus 12z cubed dv over d. Now, where's d? I'm going to consider that this is a rectangular thing. So it's 2x plus 2z plus 12z cubed. I'm going to say dz, dy, dx. Now look what happens. We usually look from the bottom here. Look at the object, the solid. This is our solid from the bottom. This one here, what's z equal to? It's equal to 0. Go through here and go to that one. So you're going to start from this one, go all the way up. What is this one here? This is z equal to 3, isn't it? This is the plane, z equal to 3. So for z, it's from 0 to 3. Then, how about dy dx? Look at the region. This is the y-axis, and this is the x-axis. If I graph it, we know that it's shown that y is 2 and x is 1. So this is our region. I took it dy over dx, so this is a region of type 1. So that means we're going to take a vertical sector. It will move from where? From x equals 0 to x equal 1. So for the x, it's from 0 to 1. How about y? What's that height? It's this one, y equals 0 up to y equal 2. So for y, it's from 0 to 2. Now you integrate from where? From inside. So this is equal to the integration from 0 to 1, integration from 0 to 2. Now we can go inside and integrate the inner part. What's the integration of 2x with respect to z? It's 2xz. Plus, what's the integration of z? Z squared over 2 goes with this 2, so you have z squared. Plus, what's the integration of z cubed? It's z4 over 4. 4 with 12 is 3z4, and this is from 0 to 3. And we say dy dx. Now this is equal to the integration from 0 to 1, integration from 0 to 2. Now let's put the 3, guys. So what do you get? 6x, then plus 9, plus 3 to the 4 is actually 81. 81, if we multiply it by 3, we get 243. Okay, and then we close. Of course, minus the 0, there is nothing. Then we say dy dx, and this is equal to the double integration 0 to 1, 0 to 2 of 6x plus this one plus 9 is 252. All of this, now we say dy dx. Now what we're going to do, we will say this is equal to the integration from 0 to 1. We start from the inside. So let's take the green. What's the integration of 6x with respect to y? It's 6xy plus 252y. And this is from 0 to 2. And then we say dx. We plug the 2, so 0 to 1. Put the 2 for, actually we're doing for y now. So put a 2 here, times 6 is 12x, plus put 2 for the y, times 2, 504. And this is dx. Now I'm left with this one. So the integration of this one is x squared over 2. So this is 6x squared plus 504 and x. And this is from 0 to 1. If we put the 1, we get 6 plus 504 and minus, of course, 0. So, and this is going to be 510. This is the answer for that part. Let's look at this one. We need to find the divergence theorem. Again, we need to find the flux. So let's find the curl F, guys. What's the curl F here? It's the partial derivative of, okay, let's look at curl F. It's the partial derivative with respect to x of x over x squared plus y squared plus z squared plus the partial derivative with respect to y of y over x squared plus y squared plus z squared plus the partial derivative with respect to z of z over x squared plus y squared plus z squared. All right, let's take the first one, guys, this one here. How do you differentiate this? It's the denominator times the derivative of the numerator, which is 1, minus the numerator, which is x, times the derivative of the denominator with respect to x. What's the derivative of x squared? It's 2x, and the rest are zeros. Over x squared plus y squared plus z squared all squared. Plus, same thing here. It's the denominator times derivative of the numerator with respect to y, which is 1, minus the numerator times derivative of the denominator with respect to y, which is 2y, divided by x squared plus y squared plus z squared, all square, plus same thing here, x squared plus y squared plus z squared, all square, and on the top you have x squared plus y squared plus z squared times 1, the denominator times derivative of the numerator, minus the numerator, which is z, times derivative of the denominator, which is 2z. This is equal to, they all the same denominator. So I'm going to take x squared plus y squared plus z squared, all square. Now look at this one, x squared plus y squared plus z squared minus 2x squared. So x squared minus 2x squared is minus x squared. So you have minus x squared plus y squared plus z squared. Same thing here, plus, you look at this one, so plus x squared. Now y squared minus 2y squared is minus y squared plus z squared. Last one is x squared plus y squared. And look at this, z squared minus 2z squared is minus z squared. So minus x squared goes with plus x squared, y squared goes with minus y squared, z squared goes with minus z squared. So what's left on the top? It's x squared plus y squared plus z squared divided by that. So if we simplify it, this all is going to go with the square, and you're left with 1 over x squared plus y squared plus z squared. This is the curve F. So the flux now is equal to the triple integration of 1 over, look, this one is considered as spherical, isn't it? We can use here the sphere, spherical. So in this one, we know in the spherical, this is equal to what? Rho square. And then we say rho square sine phi, then d rho, d phi, and d theta. Now, let's look at rho. If you look inside here, guys, I'm going to take something that represents our rho here. So the best thing probably is to take the black one. look at this here. We go all the way to the origin. This is considered as our rho, right? You are in the sphere now. This one is the inner circle. This is inner sphere, and this is the outer sphere. In the inner sphere, what do we have? Make it neatly. I want to avoid this one actually. All right, let's take this as our rho. The tip of this one, the initial is actually A, right? Because this is a sphere of radius A, the small one. A is less than B, and it ends on B. So this is the length of rho, isn't it? It's supposed to be from 0 to B, but here I'm in between these two spheres. So this is A, this is how far this one from the origin, and this is how far is this point from the origin. So when it comes to rho, it's from A to B. Now, remember, now we're going to measure the angle between the z-axis from here. This can start from here, by the way. This all moves, keep on moving to cover all this region. It will keep on moving all the way till we what? Reach to here. How much did we travel with respect to phi? Phi is the angle between rho and the z-axis all the way down. So this is from 0 to pi, because we know that from previous section that phi is maximum between 0 and phi and pi. Now, do you see that disc here, or that shell, I would say, or washer? If I rotate it completely, this will cover what? The whole, but of course, we're going to rotate it now what? Counterclockwise, so it's going to rotate this way. Full rotation. What is this? This is for theta. It's from 0 to 2 pi. This is full rotation. So that washer, when it makes full rotation from 0 to 2 pi, this will cover what? The outer sphere. Now what happens? Rho square goes with rho square, and we start the integration from inside. So this is 0 to 2 pi, 0 to pi. Now sine phi is a constant, so we don't integrate it. The integration of d rho is rho from A to B. Then d phi, d theta. Now this is our part here. Put the B, so it's going to be B minus A. Take it out. So this is equal to B minus A is a constant, can be taken out. So I'm left 0 to 2 pi, 0 to pi. Now what? We have sine phi, d phi, d theta. Now again, where do we go? We go inside. So it's equal to B minus A integration from 0 to 2 pi. Now what's the integration of sine phi? It's minus cosine phi from 0 to pi. That's the inner part. Then d theta, which is equal to B minus A integration from 0 to 2 pi. Now put the pi, so you get minus cosine pi, minus and minus becomes plus cosine 0, then d theta. Cosine pi is -1, and there is negative. Cosine 0 is 1. 1 plus 1 is 2. So this is 2 goes out. So this is equal to 2 B minus A integration from 0 to 2 pi of d theta. And we know this is 2 pi. So this is going to be 2 B minus A times 2 pi. So the answer is 4 pi B minus A. Did I say 4 pi? 4 pi B minus A. All right, this one now. We need to find the divergence theorem. So we say what? The divergence of f is equal to the derivative of this is p, with respect to x is 30xy, because the derivative of x squared is 2x times 15 is 30. The derivative of this with respect to y, this is a q, there is no y, so it's a 0. The derivative of this with respect, this is r, with respect to z, it's 0. That's it. So this 30xy is our divergence. So the flux, it's equal to triple integration of 30xy dv over d. Now, what is our d? This is the problem. Look at this. I'm going now. Graph it carefully. This is really, really confusing. The first one says z is equal x plus y. This is the upper surface. Okay. How do you graph this one, by the way? So when we say z is equal x plus y, let's take z to be 0. So what do we get? We get y is equal negative x, right? Y is equal to negative x. So y is equal negative x could be the lower one, and or it could be the top one. All right. So I prefer actually, let me remove that one. I prefer to graph it in a different way. Let's focus on z. Let x equal to 0. So what do we get? We get y is z is equal to y. Where is z equal to y? Let me make it like that in different color. Here it is. This is z equal y. Now let's take y equal to 0. So we get z equal x. Z equal x is like this one. This is actually z equal x. And then what do we have, guys? So what's going to happen? This is going to go all the way up in our direction. Then you have z equal 3. Here is a 3. So what do we get from this one? We are going to get actually this plane, or this surface. This is our surface. At the bottom here, you have z is equal x plus y, by the way. Okay. So this is like a kite thing. X equals 0, as you know, x equal to 0 is the z y plane, or the yz plane. So you see in the back, it's been cut. Huh? We're not going to go. And y equal to 0 is exactly here. So this is why there is a cut from the back. And then z equal to 3. This is the plane z equal to 3. This cut will give me z equal to 3. Also, we have x plus y equal to 2. You know, if you take this one, x plus y equal to 2, I'm going to change the color here to see how the graph looks like. Here it is. So when x is 0, y is 2. Here is 2, 1 and 2. And when y is 0, x is 2. Here is the second point. What I'm going to do, I'm going to go all the way up now, because this is a plane, guys. It's going to go all the way up. And this is going to go all the way up. This plane is going to cut this. How does the cut look like? It will look like this, guys. And it will go like that from here to this, and from here to that. And this is our shape. This is the final shape. See that? This is the shape that we are talking about. Here it is. If you need it more clearly, you can see it's like that. This is the shape that we got. All right. If I'm standing here at the ground, by the way, so this is the reflection. So the reflection of this one is going to be here. If I'm standing here, I look up. what am I looking? I'm going to look at this space, this region, right? This surface at the bottom. Who's that? This is z equal to what? X plus y. So look, I'm going to say here, so this is equal to the triple integration of 30xy. Then dv, I'm going to say dz, dy, dx, for example. Now z, if you look at the bottom, it's x plus y. So I'm going to say from x plus y. If you go all the way past this point now, so you're going to go from here, look up, you're going to go through this point, then inside, you're going to move inside the surface, and then here you're going to go up again. What is this? This is z equal to 3, isn't it? This is the plane, z equal to 3. So here is a 3. So it's a new direction. You stand down, look up, the surface is going to be like this, and this is how it goes. If you look at this, you are standing here, this is 2, and this is 2. You are somewhere here. When you look up, you're going to go through this point. Now you're going to move inside the space, the solid, then you're going to go from here. So this is z equal x plus y, which I graphed, and this one is, this is the plane z equal to 3. All righty. How about the base here? Look at the graph here. What do we have from the base? Y is 2 and x is 2. Since I made it dy dx, so I'm going to take a region of type 1. Take any horizontal line, any vertical line, sorry. The line is going to start with, from where? From x equal to 0 up to what? It's going to keep on covering till it stops here. What's this on the x-axis? Again, 2. So x from 0 to 2. Now let's look at the magnitude, the length of this. As long as you're here, this is y equal to 0. And what is this? This is y equal mx plus b. I know that b is 2, so y is equal mx plus 2. What's m, by the way? This is 2 and 0, and this is 0 and 2. So 0 minus 2, so m, 0 minus 2, then 2 minus 0, over 2 minus 0, which is negative 1. So this is y equal minus x plus 2. So for the y, from 0 to 2 minus x, or minus x plus 2. Now what do? We integrate from inside. So this will give me integration from 0 to 2. Integration from 0 to 2 minus x. This is going to give us 3xyz from x plus y to 3. Then we say dy dx, and we close that part. So this one. This is not closed yet. And this is equal to the integration from 0 to 2. Integration from 0 to 2 minus x. Now put the 3 for what? Don't forget we integrate with respect to z. So I'm going to replace that with 3. 3 times 30 is 90 xy minus 30 xy, and then x plus y. We replace z with x plus y, and all of this dy dx, which is now equal to the integration from 0 to 2, integration from 0 to 2 minus x. This is 90 xy minus 30 x squared y, then minus 30 xy squared dy dx. Now we are going to integrate this one from the inside. Sorry. Take that one. The integration from inside. So this is equal integration from 0 to 2. This integrate with respect to y. What's this? This is 9 y squared over 2. So this will give me 45 xy squared minus, same thing, y squared over 2. So 15 x squared y squared. And this one, y cubed over 3, and there is 30, so minus 10xy cubed from 0 to 2 minus x dx. Now, what do? We plug actually the 2 minus x for y. So you have 45x, then 2 minus x squared minus 15 x squared and 2 minus x squared. Just 1 second, square. Okay, so the integration with this one is y squared over 2. So we didn't integrate, we just expanded this one. 30x squared y, 30x squared y. Okay, here, y squared over 2, 49, okay. Then y squared over 2, correct. Then minus 10x 2 minus x cubed. Now, if you place y 0, that's it, is 0, and this is now what? dx. All right. Now we have to expand all of this, unfortunately. So this is the integration from 0 to 2. 45x times 4 minus 4x plus x squared minus 15x squared, then 4 minus 4x plus x squared minus 10x, then the cube of this is the cube of the first, which is 8, then the first, then 3, the square of the first, which is 4, times the second, which is negative x, then plus 3, the first, which is 2, times square of the second, which is positive x squared, and finally minus the cube of the last. And we close and we say dx. Oh God, now we have to expand this more. So 0 to 2, 45x times this is 90, 180x. Then this times that is minus 180x squared. Then the last one is plus 45x cubed. Here, this times 15, 30 and 30 is 60, so minus 60x squared. Then 15 times this is 50 again, 60 again, but plus 60 x cubed, then minus 15 x to the 4. Done with this one, let's go here. Wow. 10x times this, so minus 80x. Then minus 10 times this, so minus is plus. This is 12, so 120. So it's going to be plus 120x squared. This is 6 times 10 minus 60. And what do we have? X squared times x is x cubed. The last one, minus is a plus 10x to the 4, and all of this tx. All right. So let's see if we have space. Yes. So let's look at the highest degree, guys. 10x to the 4, and we have minus 15. So this is minus 5x to the 4. So this is equal to the integration from 0 to 2 of minus, what did I say here? I said minus 5x to the 4. Now, so this one with this one is finished. Let's look at x cubed. minus 60 with minus 60 goes away. So, but we still have this guy. So 45x cubed plus 45x cubed. So this is also done. Let's go to x squared. We have minus 80x squared, 180. This is x squared, and this is x squared. This one with this one is 60, and minus 60, they all cancel. No more x squared. Let's look at x, guys. 180x minus 80x is minus 100x. Dx. Now we integrate. So this is going to be x to the 4 over x to the 5 over 5. So this is minus x to the 5. X to the 4, so plus 45 x to the 4 over 4 minus x squared over 2. So this is 50x squared. And this is from 0 to 2. 2 to the 5 is minus 32. 2 to the 4 is 16. So if you put 16 times 45, is 720 divided by 4 is 180. So this is plus 180 minus, this is 4, so this is 200. So what do we get here? 180 minus 200 minus 32 is minus 52. This is, guys, the flux. I hope the numbers are correct. Okay, now let's go to this part. Find same thing. So we're going to find the divergence of F to find the flux. The derivative of this one with respect to x is 6xy squared. The derivative of this with respect to y is 1. The derivative of the last one with respect to z is 6xy squared. This is the divergence. This one cancels that one, and I'm left with 1. That's the divergence of F. So what's the flux equal to now? It's triple integration of dv over what? Over d. What's d now? It's this paraboloid, guys. So let's graph this one and see what do we get. The paraboloid, we know this is the paraboloid that goes up. Okay. And you can make this one here. And so this is going to go like that. And then it's going to go on the back like this. So this is our paraboloid. Then we have the plane z equal to y. Z equal to y is somehow like something like this. I'm going to graph the other one. Z equal to y, actually, it's going to be this plane that is going to cut this paraboloid. What's the result of the cut, by the way? The result of the cut is going to be something like this. See? So the final graph, guys, look like this. Let me put the XYZ here. It's the paraboloid, and here that's the upper face of it. See? And this goes like this. See, this is the shape. It's like a cup being held. All right. Now, when these two guys intersect, what's the result? The result of this circle, right? This circle is the result of the two things. Who is this at the bottom, by the way? This is the paraboloid, which is x squared plus y squared. Who's this on the top? This is the intersection between the paraboloid and the plane. So let's see what's the result of the intersection. So you have z equal x squared plus y squared, and you have z is equal to y. So x squared plus y squared is equal to y. Bring 2y here, so you have x squared plus y squared minus 2y is equal to 0. Let's complete the square here. Minus 2y, we add b over 2, which is 2 over 2, which is 1. So we add 1 and subtract 1 equal to 0. So you have x squared plus this is y minus 1 square. Move negative 1 to the other side, becomes 1. What is this? This is a circle centered at where? 0, 1, and the radius is 1. So if you go down here, guys, the result is a circle centered on the y-axis at the point 0 and 1. x0, y, and 1. This is exactly the result of the intersection. Alrighty? So the top one is z equal 2y. But when they intersect, the result is a circle that is exactly here. I'm going to grab this circle here. Our base here, this is our region base. Okay, so let me graph it with a different color so you can see it. Let's use a green. Center is x0, y1. This is the y-axis, and this is the x-axis. This is our base here. You see this one, the green one? This is our base. It's a circle. How did I know that? I did it here. So I got this. The circle centered at 0, 1, and with radius equal to 1. All right. Now, which circle is this? This is, as you know, it's nothing but this. So we have this is x squared plus y squared equal to 2y. But we know x squared is r squared. And 2, what's y equal to in the polar? It's r. Y is r sine theta. Divide by r, so r is equal to sine theta. So let's take this r, guys. So this is going to be triple integration dv. Let's look at what I'm going to do here is I'm going to consider as it's rectangular, and they move from rectangular to cylindrical. Actually, I'm going to use the cylindrical. In the cylindrical, the formula says you use what? Now, by the way, this is 1. So you have 1, then dv over d. And this is equal to the triple integration. I can replace dv with what? dz. Remember, in the cylindrical, we use dz, then r, dr, d theta, right? This is the cylindrical one from the previous section. Okay, now how about z? From where? Who's that? This is z, the bottom one. If you stand here and you look up, you're going to cross here at z equal x squared plus y squared is what? Is r squared. So the z is from r squared up to a to z equal to what? 2y. So this is 2. Y is what? R sine theta. So this is up to 2r sine theta. That's the top one for z. Now for r, this one is starting from 0 up to what? What is this? As long as you are here, you are at r equal to what? Sine theta. So this is from 0 to 2 sine theta. How about theta? To cover all of this, you have to start from 0 up to here. So it's from 0 to pi. And this is, guys, the result of the limits of integration. Now we start from inside. We start with dz, actually. So here is with dz. So this is equal to integration from 0 to pi, integration from 0 to 2 sine theta. The integration of z, dz is z. And then we say from r square to 2r sine theta. And then r dr d theta. And this is equal integration from 0 to pi, integration from 0 to 2 sine theta. Now put this one here, you'll get 2r sine theta, and then minus, put r square, here is r square, and then all of this r dr d theta. And this is equal to the integration from 0 to pi, integration from 0 to 2 sine theta. Now, r with r is r square. Integrated, you get r cubed over 3. So this is 2r cubed over 3 minus r squared times r is r cubed. Integrated, you get r4 over 4. All right, we're done with this one. And then we say what? dr d theta. My apology, actually, I did integrate. So let's erase this one. I don't know why I'm writing this. I already integrated. So let me fix this one. So the integration of this, as I said, it's r cubed over 3. So 2 over 3 r cubed sine theta minus r4 over 4. And this is from 0 to 2 sine theta. And then what do we say? d theta. Put the sine theta here. You will get integration from 0 to pi. Then you have 2 over 3 r cubed. We are replacing r with 2 sine theta. Sorry, let me replace this one properly. If I put 2 sine theta cubed, it will get 8 sine cube theta. 8 sine cube theta minus, if I put it here, I will get 16 over 4, which is 4 sine 4 theta, all of that d theta. And then we finish all of that, guys. This is a long integral, and we get actually after that, it's really, really messy and very long. You get pi over 2. You see, this is going to be really long. So, so this will be at the end pi over 2. You need to go back to the sine cube. Remember the sine cube, how we do it? You have to make it sine square and sine. So, and sine to the 4, you have to do it yourself. So it's really a long integration for these two. So you need to do them properly. Okay. And this is, guys, how you integrate this one. So because we multiply it, so this is r square, yeah. So this is, guys, how you integrate and then finish it to get to the final answer. So this is how you use divergence theorem, and this is the last section of this chapter. Congratulations, we finished that. The point is, I used here all different styles of integrals to find the flux in three-dimensional integral. Have a good day, guys. We'll see you. I think that's the end of it. Thank you for joining me, guys. I hope you enjoyed it. I hope you understand everything here. And maybe the integrals is something you have to work on at the end in this question, but the rest is supposed to be doable. Have a good day.